Heat transfer example problem. Natural convection between concentric cylinders. A solar collector consists of a thin horizontal aluminum tube with a diameter of 5 centimeters enclosed in a thin concentric glass tube with a diameter of 10 centimeters. Water is heated as it flows through the aluminum tube by solar radiation at a net rate of 30 watts per 1 meter of tube. The annular space between the aluminum and glass tubes is filled with air at atmospheric pressure. The ambient temperature of the outside air is 20 degrees Celsius. The pump circulating the water fails during a clear day, and the water temperature in the tube starts rising. When steady state is reached, determine the temperature of the glass tube for part A and the temperature of the aluminum tube for part B. Our first assumption for this problem is steady two-dimensional flow of air between the cylinders and outside the outer cylinder due to natural convection only. Our second assumption is constant properties. However, note that the density must be changing for natural convection to occur, but that we use a density at the mean temperature for our calculations. Our third assumption is that the net radiation specified is constant. Our fourth assumption is that the cylinders are horizontal with uniform surface temperatures where correlations are reasonably accurate. Our fifth assumption is that the air is an ideal gas at atmospheric pressure, which will be used to look up properties. Clearly, these are some significant assumptions, and we should only expect an accuracy of about plus or minus 20% for our results. To find the steady-state cylinder temperatures, we first apply an energy balance on the inner aluminum cylinder. Based on this, when the water stops flowing, the net solar radiation into the inner aluminum tube must equal the convection across the annular air gap. Second, we perform an energy balance on the outer glass cylinder. Based on this, the convection across the annular air gap must equal the convection from the outer surface to the surrounding environment. Alternatively, if we use a resistance analogy to model this system, the two thermal resistances are in series and the current or heat transfer through each is the same. During normal operation, when water is flowing through the pipe, most of the solar radiation would instead go into heating the water flowing in the tube, and the whole system would operate at lower temperatures. To model the natural convection from the outer surface, we use Newton's law of cooling and solve for the outer temperature as shown. To model the natural convection for the annulus, we use an effective thermal conductivity that accounts for the conduction and advection across the air gap and solve for the inner temperature as shown. For part A, to calculate the temperature of the outer glass tube, we need to obtain an average convection coefficient from a Nusselt number correlation. To do so, we first need to determine the flow regime from the Rayleigh number, which is proportional to the buoyancy force and the strength of the natural convection. This requires that we know the temperature of the outer tube that we are solving for. Thus, this calculation requires an iterative technique. To automate this process, I used ease for my calculations, and we will use the final converged temperature for our initial guess to show the necessary calculations. Substituting in values, we get a Rayleigh number based on outer diameter of 1.90 times 10 to the 6th. Note that for these calculations, we are using properties evaluated at the film temperature of 304 Kelvin, which again is calculated using our initial guess for the outer temperature. Referring to our textbook, we select the average Nusselt number correlation for natural convection over a long horizontal cylinder from Churchill and Chu that is valid for our flow conditions. Substituting in values, we get an average Nusselt number of 17.5, an average heat transfer coefficient of 4.5 watts per meter squared Kelvin, and finally an outer surface temperature of 41.1 degrees Celsius, which agrees with our initial guess, thus confirming that the solution has converged. If we had guessed something else, our temperatures would not agree and we would repeat the calculation until they did so. For part B, to calculate the temperature of the inner aluminum tube, we will use a correlation for an effective thermal conductivity for the natural convection in the annulus. To do so, we again need to determine the flow regime from the Rayleigh number. Once again, this requires that we know the temperature of the inner tube that we are solving for. Thus, this calculation also requires an iterative technique. To automate this process, I used ease for my calculations, and we will use the final converged temperature for our initial guess to show the necessary calculations. Substituting in values, we get a Rayleigh number based on a characteristic length for the annulus of 5.6 times 10 to the third. Note that for these calculations, we are using properties evaluated at the mean temperature of 336 Kelvin, which again is calculated using our initial guess for the inner temperature. Referring to our textbook, we select the effective thermal conductivity correlation for natural convection in an annulus from Rathby and Hollins that is valid for our flow conditions. Note that if the Rayleigh number is below 100, we would have conduction only and would just use the actual thermal conductivity to calculate the temperature. Substituting in values, we get an effective thermal conductivity of 0.0775 watts per meter Kelvin and an inner surface temperature of 83.8 degrees Celsius, which agrees with our initial guess, thus confirming that the solution has converged. Again, if we had guessed something else, our temperatures would not agree, and we would repeat the calculation until they did so.